John here. I'd like to open by thanking my Patreons. I mean, I just set this up, and already a couple of people have decided to try to help support this channel. I really appreciate it. So the other day, a couple of weeks ago, I stumbled across this board. It's been sitting around the basement, and I notice it every now and then. But it kind of came to realization the other day that 40 years ago, right now, in the fall, during my freshman year semester in college, I designed this board. Then I saved up my pennies, and in the springtime of 1982, and summer most likely, I was able to get all these sockets and the chips and stuff and solder this thing together and debug it. As you can look at, probably required a little bit of effort there. This I was learning how to solder these little wires and stuff at that time as well. I had done some work before that, but it was my real serious first real foray into this kind of work here. And it's funny because this thing became my daily driver for 6 years. Came to life in 1982. And this is the board. The Z80 that was, I've long since scrounged it for parts, probably even rebuilt it at one point. This chip over here looks much newer. I don't know, there's a date code in here that starts with an 88, so it might be, maybe I broke it or something and I had to replace this chip or something. Anyway, the point is this board was my daily driver for all my years in college, all the way up through my master's degree that I received in 1987. So this has a lot of mileage on it, and it definitely worked quite flawlessly all that time. I had dual 8-inch single density floppies, and I had ported CPM 2.2 to run on it, and it was just a fantastic machine. I had no interest whatsoever in upgrading to an IBM PC for the like $3,000 it would have cost to do that. This was much cheaper to make one of these by hand. And quite frankly, I mean, this thing ran at 2 megahertz, and the IBM PC ran at like 4.4 megahertz. And I didn't need the software. I mean, there was more than enough CPM software lingering around that was easily accessible. So I really had no reason to until like the end of the 80s when, you get your first job and stuff, and you then need to have the compatible versions of the software to run your stuff on your own if you want to. Anyway, it's amazing this thing ever worked, especially as well as it did with this giant bundle of wires in here. If you take something like this on, don't do it like this. This is just wrong. If you do this, right, now these are all just what we call a pad per hole plug board or breadboard. There's no ground plane in here, and every little pin that needs to be connected to another pin, you have to put a little wire on here. Now I used wire wrap wire for this, but obviously those are not wire wrap sockets. It was because wire wrap sockets stick out the back really far, and I had delusions of needing to plug many cards into a card cage back in the day. And I mean, they only had 16 or like 20 slots in those things back in those days. You didn't want to waste every other one by having pins that stick out the back really far. Plus, they would stick together. They could short out and come together if you tinker around inside the machine, like I did all the time. So this seemed to me to be the more long-term viable way to do this. Anyway, so what happens is if you don't have a ground plane and you're running traces around, there's nowhere for the energy to go with it. I mean, look at the physics of the situation. When you're running electrons through a wire and you're changing the rate of flow, like when you go from a binary 0 to a binary 1 over the course of time, what happens is you're creating or sometimes reversing the direction of a magnetic field, and that is going to want to induce a current into some nearby, a conductive material, which in this case is all these wires. So it's going through this bundle of wires here. These are mostly address lines. The red ones over here I can see because this is a Z80. The data lines are over here. The address lines go up and around like that. These address lines would interfere with each other or the data lines right in this big bundle. The blue ones, I suspect, are like control signals, like read and write and stuff like that, maybe. Or maybe those are the white ones. I got white ones in here too. I don't know what I was thinking when I put this thing together. I certainly didn't understand crosstalk is the general term for this potential problem in this board. Somehow I got away with it. I think the reason I got away with it is because the address lines and data lines pretty much all change at the same time, and then they're all stable at the same time, roughly speaking. So if they do interfere with each other, they do it at a time where it really doesn't matter. You know, if the Z80 isn't really looking at the signals and the values and the data that are on all these wires, then it's okay for them to be wrong, right? It's only when the Z80 says, hey, I care about what's out there, that it needs to be stable, static, with nothing going on and changing to cause interference. And it turns out that the Z80 does have these long periods of stability right before it puts its eyeball out here and looks around at what's going on. So that's probably why this worked. The faster your clock goes, the worse this mess gets, right? So what do we got here? We have a bunch of chips that run the, this is an S100 bus card, right? 100 pins here, 50 on the top, 50 on the bottom. You can see a bunch of wires going to this half of the bus over here on the right. These are the address and data lines. All these chips here are like driver chips because the, you know, remember these, back in the day, the S100, you could have 20 some cards on a bus. These had to be very strong driver chips in order to get enough voltage and current and overcome all the capacitance on that bus. So these were high current driver chips to make sure that when the Z80 says make this a 1, wham, it makes it a 1 and shoves it down on the bus lines, right? So that's what all these chips were doing here. I don't know what these were over here. There's little tiny, I don't know if you read these. I wrote on here what the types of chips are as I removed them and scrounged them out of here. Some of them I didn't label. Good luck figuring that out. These two I know, these would have been AY3 1015D UARTs that you could buy over the counter at the Radio Shack that was within bike riding distance from my house. They were dirt cheap and they came with great documentation. I had used them before I did this board for other things, and I knew how to use them, so that's what got on this board. These over here, anyway, the point is these are labeled. These are would have been some for LS32s. I think those are OR gates for whatever they were doing over there. This would have been the timing system. There's a crystal right there. This would have been generating my 2 megahertz clock, some glue logic up here. This chip would have probably been an LS245 bidirectional bus transceiver because I can see the way these wires connect up and go over to these UART chips. That's where the data bus lines would have been on the UARTs, and I know where the data bus lines are on the Z80, which are these red wires here, so they kind of wind around down through this chip and over to the UARTs. And you'd used to use these because the Z80 could only drive so many chips. You'd have to put a driver on there to offload the work that the Z80 has to do to make sure that there's enough signal. It retains its integrity if you're going to run a lot of chips with it. This was probably not necessary in this particular design, but who knows? I felt the need to put it on there. This dip switch here, you can tell by these little pull-up resistors are over here. These were used to select things like 7 bits versus 8 bits, and do I want even or odd parity, no, or even no parity, 8, none, 1. You'd toggle these switches together to select those options. How many stop bits and things like that on these UARTs. And there's only one switch, so most likely, if we look closely, yeah, there are. See these little red wires back here? Get the glare off of this thing. Connects these dip switches, which are here, to both of these UARTs. So I had no way to select one option for one of the UARTs and different options for the others. Both of these had to have the same configuration. Probably due to a lack of space. Well, I don't know. I was not very careful about spacing in here. I wanted to leave more than enough room for all the wires and stuff, I guess. Anyway, so I didn't have room over here for the other dip switch. Maybe I could have put another one there. I don't know. Move this over a little. Whatever. I don't know. These are LS193s. as labeled, these would have been counters, and this switch here most likely would have been a value. Like, every time the LS193s counted down to a 0, they would be reloaded with a new value, and they would then count down back to 0, and this switch here would have been the value to load, and that would have then determined the bit rate that these two UARTs would have used. Again, they probably both use the exact same clock. I'm not going to trace all the wires out to figure that out. But most likely, given that there's only one dip switch over here, that's 99% odds what was going on. I have no idea what this LS138 was doing. It's an a 3 to 8 line decoder chip. Some unmarked chips, I don't know what those did. An LS30 and LS32, I don't know. Beats me. Something to do with the serial port, most likely. This, if memory serves, would have been a ribbon cable dip header, so the cable would have plugged in on here and run off the back to a DB25 or a pair of those for the serial ports. A couple of voltage regulators. These are all 5 volts. There's a 12 volt. These would have been this RS232 line driver chips, which would need the 12 and negative 12 volts. Maybe there's another regulator on here. This is another 5 volt. I don't know. I would have expected to see a negative 12 volt regulator in here. There are some resistors and a transistor there. Maybe this is a negative 12 volt in a smaller sized package. I don't know. Little tantalum capacitor ready to blow up right there. Right? You gotta be careful when you use tantalum capacitors because they have such a low impedance that the voltage on your board, when it goes from 0 to whatever, the voltage ramps up. These can take in current at such a high rate of speed that instantaneously it can overheat inside and cause it to heat up very quickly and essentially explode. So the thing will pop open like a ladyfinger firecracker, and the epoxy goes flying all over the place. I've had that happen to me. You don't want that to happen. Unless you know what you're doing, don't use tantalum. I can assure you I did not know what I was doing when I put that in there. These were very popular back in the day for power filtering capacitors and stuff like that. Certainly, it was probably not needed. You could just put some ceramic capacitors in there in parallel with these electrolytics for filtering, and it would have been fine. Nowadays, we can buy ceramic capacitors at a very large values. And that's the thing about tantalum. You could get, your 20, 30, 40 microfarads on them. But you can get those in ceramics today, which don't have this inrush current problem, and they won't explode. I bring up the exploding tantalum problem because one of my old S100 card cages, Calcomp box, I fired it up one day, and every one of the tantalums all at once blew up in there. Epoxy all over the place. I'm like, oh, that wasn't so nice. Most likely due to the fact that as I turned the power switch on, it probably, as the contacts came together on the line current, it probably arced on and off many times and caused, a weird voltage rise in the power supply, causing inrush current to blow them all up. That was a little depressing. But it would be no big deal to take them out and replace them, or even replace them with ceramics, I guess. Anyhow, anybody got any ideas, let me know. What do you do with those things? Not that I expect to get a lot of use out of it. Why? Because I've already scrounged this board for all of its parts, and it's not ever going to go back together again. Because I don't think I ever drew up a schematic for this thing either. Back in those days, I kind of just wired these up in my head. I did have a schematic. Like I said, I was drawing it up in the fall semester of my freshman year of this section over here. Took me forever to figure this thing out. Decide what I wanted to do. Read lots of books. What do I got to put in here? How many milliamps do I need? It was a lot of studying. And this was drawn up. But then as I go, I just said, I need another UART. And I'd flip it over and say, okay, hook up these wires and stuff. So by the time this is done, I guarantee you there's no drawings of this thing anywhere. But anyway, that was the Z80 board. My 40-year reunion with my college computer right here, okay? Now, I did another video a couple of years ago on this board right here. This is the static memory board for that machine, okay? Now, this board, each one of these chips is 2K bytes. That's it. This EEPROM was probably also 2K. If I look, I just stuck one in that I had lying around. I don't know how well this shows up. This has got a 1979 date on it. All right. And yeah, before everybody says, well, you need to put a cover on that so the UV light doesn't get in there and erase it. That's okay, because I happen to know this chip is erased. And even if it did work, guess what? On this machine, it had a homemade floppy disk controller that I scrounged to the point where the circuit board itself was scrounged. So that I can't put back together again. I'd have to start over. And therefore, even if I had the right code in my old boot ROM, it's there to control a board that no longer exists. Anyway, in the other video, I'll put a link to it in the description below this one. I do plug this into an IMSI 8080 that a friend of mine gave me, I don't know, 25, 30 years ago. And this card still works. And there's a circuit over here. I explain how it works. That selects the boot ROM that it boots out of, and then it deselects the boot ROM, and it goes away. So there's only then just RAM left in the system, which is, I thought it was a pretty neat idea. It's called Phantom ROM, or we call it a shadow BIOS, that sort of thing. It's because you don't, in these days, the machine could only address 64K of RAM total. You don't want to waste 2K of it by leaving an old boot ROM sitting around hogging up the space after the machine is running, because you don't need it anymore. Modern PCs use it because these ROMs run slower than the RAMs. So one of the things you do, like when you have a shadow BIOS on a PC, is you read in the ROM data, you copy it into the RAM at a slow speed, then you throw the ROM away, and you then proceed to execute the code out of the RAM, because at that point the CPU can run faster. Okay, so this board would have been the second one that I built, and you can see the wiring on here. This down here is a little sloppy, and if I recall correctly, this card originally had one row of chips up here. I couldn't afford more. And these chips over here were vertical over here, right? And in fact, if you kind of look closely, you can see these vertical lines of these holes on these pads here are all full of solder. That's because originally these four driver chips here, again, they have to drive the bus just like the CPU. They would have been vertical like this over here. And it wasn't until later that I realized that was a really dumb choice, because with that, I couldn't put more RAM chips in here. I had to start a whole new board. And, God forbid I shell out $20 for one of these bare, what is this, Vector board, or whoever made these things. Is there a label on here? Yeah, Vector right there. The pad per hole Vector board. And so what I did is I unsoldered these chips and re-put them over here to get them out of the way, and then I can add this second row over here. So 16K up here, and I used that for a while. Then I went to 32K. When I outgrew 32K, I needed 64K, so I made a whole nother board. Notice this one does not have a boot ROM over there. I don't need it. So this board would have responded to the high part of the address space. Addresses from 32K up to 64K. This would have responded to addresses from 0 up to 32K. Okay. You can also see that my technique improved quite significantly, especially compared to this thing. Anyway, yeah. So looking at some of the date codes on these chips, and I think these are the original RAM chips. I'm not sure if these are the boards that they were in. It might be that I ended up reversing them over the course of time, because I did salvage all these chips at one point for other projects, and then later on I put them back in here. Point is, they could have gotten rearranged. And if I check the date codes, like on this board here, they all start with 83. So this would have been done, 1 year later. I mowed a lot of lawns, saved up my money, and bought another 32K, and probably spent the summer of 83, or maybe the spring, building this card so that I could max out the memory of my machine at 64K. Now, somewhere in graduate school, I decided it would be neat to have a machine that ran with virtual memory. And I built this card. See, I still had my technique happening there. I really like this. It's kind of like sewing and weaving between all the pins. And these are, again, wire wrap wires. In this particular technique, what I did is, if you buy the wire wrapping tool from Radio Shack, which I guess no longer exists, it came with a special stripper in the handle like this, it's loose. All right. Now, if you look closely at this one, let me get rid of this out of the way. It's got a little notch in a piece of metal. All right. Now, the key with this is that on its own, you don't have a, it's not like mounted on the handle with this giant thing in your way and all that. Some tools are that way. This one, and don't lose it because it's easy to lose if you don't always put it back in the handle. The neat thing about this is if you have a wire that's soldered on like one of these pins and you've got, your whole spool might be over here, you can reach in there and strip and push the insulation away and kind of compress it down on both ends. Wrap it around the pin once by hand. And that's not really what they mean when they say wire wrap, and I know it. This tool is meant for a thing with a really long pin that you slide on and it wraps it around this way. It's got a little hole in here and stuff like that. I'm sure there's videos on YouTube that show you how to use wire wrapping tools. I kind of abuse it is my point. So what I did is I would strip the wire back, wrap it around by hand once with like a screwdriver or something like that, and kind of pull it tight and just reach in there with a soldering iron and dab the solder, which heats up immediately because you're only heating up the pin and the piece of this, with that Kynar wire or whatever they call that, the wire wrap wire. And it solders very quickly. A teeny amount of solder on there. And while it's soldering, what happens is, because I've compressed the insulation away from where I've cut it, I kind of like go in and kind of push it back and forth and kind of push it apart to get the wrap in there. The heat causes all the insulation to run back again really close up against these pins. So what happens is there's absolutely none of this wire or the insulation that is peeled away and exposing the wire in here so it doesn't short out against everything nearby, which is definitely what happens if you're going to use like phone wire. This down here is, your little, I called it phone wire or Beltel wire. This is like the wire that's inside almost a Cat 5 cable. If it has solid core, this is solid core wire, and my buddies and I always called it Beltel wire. This is a different kind of insulation. It's more rubber, or maybe it's PVC, I don't know. But when you heat this kind of wire up, all that happens is the insulation melts and it runs away from where you're soldering, creates a big disaster area. Now, why did I use it? Well, I used it in this case because it's a much bigger gauge. So in here, in fact, it's naked here. I just stripped all the insulation off. If you can see that, these are the power bus lines that provide power to all these chips. You need a nice low impedance power system in order to get enough current into this thing. These wire wrap wires take almost no current at all. In fact, these are probably all MOS signals or even LS signals, moving like 0.5 milliamps, okay? Meanwhile, the rest of this is probably moving, 1 or 2 amps of current through there. So you need a bigger wire, that's why. So anyway, what's up with this thing? Why am I on here? Well, this would have been a National Semiconductor 32016. 16 physical bit address bus on a 32-bit processor, okay? This was, the low-cost version. This would have been a timing control unit. You could tell because there's a crystal there, and it's 24 pins, if I recall correctly. I probably put the CPU here. This would have been a memory management unit for the virtual memory. This, I don't remember if this was some sort of an interrupt vector controller or even a floating point unit possibly was in here. Some glue logic. These 20 pins would have been like, 74LS240 or 244 or 245, the bus driver chips. Again, there's a lot of chips over here, so you needed to put, maybe they were necessary, I don't know. I certainly thought they were. I needed to have some bus drivers in order to isolate and make sure there's enough drive capacity to run all these chips from the lowly little MMU over here. I have no idea what this was. Probably a UART, but the problem with this being a UART is I don't see any wires coming out of here that would have been connected to the UART in order to, hook it up to a serial terminal or something. I don't know. Beats me. These would have been EEPROMs that it boots off of, and the rest of these would have been static RAMs, okay? Now, these static RAM sockets here, look at these. They're bigger than the ones over here, okay? I would have built this, if memory serves, I made this when I was in grad school. Either the Christmas of 86 or possibly the Christmas of 87, I can't remember. And I did get it all to work. I had virtual memory going, and I had little processes that could spawn other processes and create address spaces and all that. A lot of fun I had with this thing. Obviously, long since scrounged the chips into other projects. But these sockets, like I said, are bigger than the ones over here, right? These are 24 pin sockets. These have 2K of static RAM in each one of these chips. These are 28 pin sockets. So I honestly, I can't remember what size. I could probably look it up. These would have had more like 32K in each one, or maybe even 64. I don't know. Or maybe I'm remembering wrong and they only had 16 or even 8K. I don't know. But they would have had a lot more memory per chip in this system than there was in my old Z80 system. Which, by the way, I used to write all the assembly language code to run on here. A really nice person uh, posted a National Semiconductor 32K assembler to some CPM bulletin board that I had access to, and I was able to download his assembler, and I wrote all my code for this thing in 32K assembler at that time. So by the late 80s, we started seeing static RAMs that were much bigger than we did in 1981, right? These 2K jobbies were around in the 70s. And I don't know, they cost a couple of dollars a piece. And that was a lot of lawns to mow in order to save up enough money to buy those. These probably were the same price, and they had 8 to 16 times the memory on them that they did at the beginning of the 80s. So, I see these things sitting around. I'm like, oh, maybe I should put one of these back together and get it running again. And I'm like, I don't really remember how these worked. And like I said, I kind of probably put this together based on, just looking at the data book for the chips and saying, well, I know I need to hook the address bus up to all these chips, and I don't need to hook up the data bus to all these chips, and just kind of make it up as I go. Uh, no schematic means hard to program. Talk about right to repair. Yeah, you could repair this if you want to trace every one of these wires and figure out what they're all for. I mean, I kind of remember the general gist, but no thanks, right? So, what would happen, I wondered, if I were to build one of these with the bigger memory chips? I wouldn't need these boards, right? If one chip was this whole board, I could eliminate all the time it takes to make one of these, right? Or if one chip was two of those boards, I could get rid of them both, right? If I get rid of them both, I don't need any of these chips here to drive a bus, because I wouldn't need the bus to hook up the other memory boards. I could just put the memory right on here. These UARTs, these older UARTs, had single port. There was a single UART in each one of these chips. And if you want a dual port UART, even in 1980, you could have used the Z80 serial I/O controller chip, which would have had two serial UARTs in one chip. Now, why didn't I do that back then? Probably because, if I recall correctly, I couldn't get Z80 data books. They were hard to come by. And we didn't have an internet like today, people. I couldn't just go Google it and download the thing. I think they were also much more expensive than these little cheapy things. And like I said, I knew how to use these, so there's a lot to go for that, really. If you know how to use something already, there's a lot of bias right there to just say, I'm going to use this because I know what I'm doing. If I use the other one, I'm diving into some sort of new risk that I don't understand. It might not work. So that's probably what I did there. Today, no, I would go with the Z80 chip. It's designed to hook directly to the Z80. It would eliminate this, eliminate that, eliminate that. It also has some clock divider logic in it. It's not great, but it has some. It's also got a programmable way to set the number of bits. So this goes, that goes, no, 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 no. All this disappears. I don't know what these things were doing, but the Z80 SIO, you can just hook directly to RS-232 line drivers. And by the end of the 80s, you had the Max 232 chip out, where you'd have single chip with both the transmit and the receive drivers in them. So again, if I wanted to stay 80s era genuine, I got to have a single chip replace all this over here, and one single chip replacing these two. So I restating, a single chip or two chips to replace this whole lot. And because all this disappears, because I have no bus, I'm down to a board that would be about that big, right? Now, if I could put all this on a board that's only 100 millimeters square, and I didn't really want to wire up all these wires and stuff on here, I could draw one up and route the board with a nice tool like KiCad and order it from one of those prototype houses for either $2 or $8 if I needed a 4-layer board, right? The 4-layer boards from like JLC PCB and PCBWay and so on. Those are like $8. And you get 5 of them for $8. Well, a few evenings later, I said, you know, if I wanted to build a board using all through-hole parts, and I allow myself to use the one big static RAM chip, so I don't have to have 32 of these chips over here. You know, can it be done? Yeah, the answer is yes, even with all through-hole parts. Okay. Now, before you call me out on this not so through-hole SD card, I got a video on how to solder this thing in. These can be somewhat tricky, and I had kind of fumbled it in that other video, by the way. So you can see how I did it, and I was able to get the thing to work. The problem with this board is, how do you hook up a storage area? Where do your disk drives go? You know, back 35 years ago, I had a whole nother one of these S100 boards that had a Western Digital 1791 or 1771 probably controller on it for my 8-inch floppy drives, and that's a lot more chips. And I really wanted it to fit into one board, and I thought it would be kind of fun to do this, throw together the video I'm recording right now, or I'm introducing right now, and let other people be able to make these too, especially if you only know how to solder through hole. Because, building back in those days, through hole was much easier. You can easily poke a soldering iron on all these. If you can solder at all, you can do through hole. And, I decided I would use an SD card instead of the floppies. All right, 2 reasons. One, I'm gonna fit all the Western Digital chips to run the floppy controller, and yeah, I could have put another card on top, and who knows, I still could. That's what this bus connector is for over here. Or I can just use an SD card for my floppy drive instead. Now, a lot of people that do retro Z80 projects use a compact flash card, a CF card. Now, the problem with CF cards is they're really big. Relative to the size of a micro SD, they're really big. And the carriers require headers that are on the order of, actually the headers are this big if you're going to use a full-on IDE or a PATA connector, because that's what they're really designed for. SD cards are the same pinout as a PATA IDE drive, and the IDE drives fit into a connector that's like this. The SD card have a higher density socket. It's only about half the size of this one. Pins are closer together, but it's still really big, and I would need to find a place on the board to put it. You could say maybe put it over here, and it would stick off to the side. And well, the problem is if you look at the connectors and stuff that you can go out and buy, they are relatively big. There's only one that I found that was actually through hole, and it would have been viable, but I still would have had a hard time finding a place to put it on this board. Plus, the CF cards cost more money, and I think Sony or whoever was the last company that actually used them just announced they're no longer going to be building products that use CF cards. So the CF card is dying. All right, we're beginning of the end for the CF cards. They have much smaller amounts of memory on one of those cards, and they cost like $20. This costs like $2. This is a Micro Center house brand SD card. This system, as you'll see, is going to run super slow. So you could buy the slowest SD card ever manufactured, and it'll work fine for this particular project. Where am I on about the SD card? So in order to address anyone that wants to try and building one of these that is not, surface mount inclined or doesn't want to take it on, or maybe try taking it on anyway. Because like I said, you buy one of these boards and ship it over, you're going to get 5 of them. You can certainly try to solder this thing on, and if you fail, throw the board in the garbage so no one will ever know. And then take one of the other 4 boards you have and put one of these on here. Well, this is a SparkFun, what is this thing? It's a Dev 13743. Anyway, this will be in the design files for this. And I soldered on a header like, one of these things like you might see on a not a Raspberry Pi, on an Arduino or something, right? One of these headers that has, you know, the female header with all the holes, and it just sits on top of this thing like so. And if you plug it in like that, this is the Z80 in this particular design does not know the difference between whether you put this thing in here and use the card in here or you put it in here. So you can leave this SD socket off the board design. Now you're 100% through hole. So anyone who can do through hole can put this whole thing together. Go over to SparkFun for $10. You dig yourself out of the problem of soldering in this thing over here. All right, and this will boot and run fine. I can demonstrate that at some point. It'll be subject of another video, and it'll work either way. So you could do this if you really wanted to. If you really wanted to experience the whole retro scene for real, a la 1982 or 81 or whatever year all this stuff really ties to. So anyway, so this board, it's got, I chose to use a 10 megahertz Z80 and a 10 megahertz SIO over here, and run it a little faster. Because I can. It's like the same price. Why not? You can just as easily put a 2 megahertz Z80 in here and it'll definitely work. Or you can change one of these oscillators and run the, even if you got a 10 megahertz, you can run it at 2 megahertz. The Z80s doesn't care if you run it slower than the rated speed. You just can't run it faster, or you at least shouldn't. If you overclock it, it may or may not work okay. So this particular board is fully populated, and I don't know, the camera probably doesn't show it very well at all. This is a counter timer controller, and I put this thing in here so that I can run the SIO at different bit rates, and I can program this to say, or make it run fast or slow. And the problem with this particular chip is, you know, there's a silicon shortage going on right now. I could not buy a CTC that runs at 10 megahertz. So this CTC is an 8 megahertz CTC. So as assembled right now, I got 10 megahertz Z80, 10 megahertz SIO. The whole thing will run at 10 megahertz, but this won't. So this oscillator in here, again, I doubt you can see that in the camera, or it might be blurry up close like this, is an 8 megahertz clock. Right, so to satisfy the needs of the CTC. These are the usual glue logic over here, and what do I got on here? These headers are for RS-232 ports. I got 2 serial ports. This over here is the Max 232 style line driver. So I don't need 2 chips, I only need 1. And all these capacitors in here are used as part of a voltage pump in this chip here, so that it can generate its own negative 12 and positive 12 voltage, all from the 5-volt supply that comes in on this USB connector. So this is a power-only USB connector on here to run the whole board. Again, super convenient. Who doesn't have a USB power supply lying around, right? So you can easily plug this thing in, power it up. There's your serial driver. These big chips here are 8-port latches that are used to operate this IBM PC parallel port compatible Centronics printer port right here. And you can make a ribbon cable and break this directly into DB25, which is pinned exactly like it is on a PC. And the reason I did that was so that you can then use the standard IBM PC to Centronics adapter cables that are all over the place, and plug it directly into a Centronics type connector on your Epson RX80 that you might still have lying around. I'm just saying. These two are pinned so that if you watch my IDC video that I posted a few weeks ago, that was me making cables for these. These map directly to the DB9s. That you need if you want to hook these up to a serial port, a la the IBM PC COM port style connectors. These are 3-wire serial ports, okay? It only has transmit, receive, and ground hooked up to these headers in order to keep it simple. Otherwise, I would have needed more driver chips, and I'm kind of out of space here. So I said, good enough. Back in the early 80s, that's all anybody used anyway. The rest of these chips over here are the glue logic and the select logic, so that when the Z80 outputs an address, it knows each one of these different chips. It says, oh, you need to respond, and so on. So these are the address decoders and stuff like that, and glue logic to support the needs of these particular chips. So when you're done with all that, if you wanted to make one of these, it turns out you can write standalone programs in here, do anything you want. I decided to port CPM 2.2 over to run on here, and there's a lot of source and how-to pages and stuff all over the internet on how to do that. If you start from the beginning, honestly, I think you'd be better off. I'll go over the process on how to do just that in some other videos, and how to configure CPM to run on an SD card instead of an 8-inch floppy. There's some design configurations you need to make, but it works just fine and dandy. Boots right up, and the first thing I did, of course, is run the Colossal Cave Adventure game, because, you know, that was... I spent a lot of time playing around with that in like 1980, and when I was in high school, and that to me was like the coolest game ever. All text-based adventure game. A lot of people probably know Zork, which came along later. The Colossal Cave was the original version, as far as I know, of that type of game. And it's interesting because around 1980 is when we had things like Pac-Man and you know, other video games became really popular in arcades, and all that all kind of started right in that era. And you know, sure, I went and played all those games, but I found something sorely lacking with the graphic games that was incredibly cool with something like the Colossal Cave Adventure. And I never really got into video games. You know, I thank the stars, because if you spend all your time playing video games, you don't have time to wire up something like this. Okay, so I credit my lack of interest in graphic video games with having the time and interest to be able to build things like this. Okay. So this is the my intro to a series that I'm going to go over all my design decisions and stuff, why I did what I did, and where to get all these parts and how to put this thing together based on the exact design of this. Okay. I mean, I remember how most of this works, and it's the simplest possible way. Hook the address bus up to the address lines on the S100, hook the data up to the data lines. And there's a lot of boards from that era that were relatively simple, just like this, whose designs are now all online, and you can go and see what how they worked as well. Okay, so thanks for watching, and look forward to seeing you again later. If you want to see more of this series, let me know in the comments below, or hit thumbs up. I have had some comments and questions about this because the design files have been on my GitHub repo for a while. I'll put a link to that in the description below if you want to have a look-see before we get into the details. Some people were asking a lot of questions about it, so I'm definitely inclined to go ahead and you know, whatever, record up a series on how to do all this stuff. Let me know if you want to try building one of these. I'd love to hear your experience, or maybe you got some better ideas. Oh, I should have done this, or I could have done that. We could always revise the design and update the files if I miss something. So, thanks for watching. See you next time.